Hi everyone. So in this tutorial, we're going to discuss the proper way to make measurements. The way that we record measurements is actually extremely important. It should give the reader an idea of the scale that was used to make the measurement in the first place, and it should give the reader an idea as to how certain the data is when they look at it. And so let's actually practice making a couple of measurements and then discuss more or less what that implies about the measurement itself. So let's have a look first at this top ruler over here. I'm going to measure this red paper clip. Notice that this ruler goes from 0 to 10 centimeters, and there are no divisions in between. So what that means is if I take a look at the length of the paper clip, then it falls somewhere between 2 and 3 centimeters. So if I were going to have to write this down in a lab notebook, this paper clip would measure 2 point something centimeters. Unfortunately, though, I'm going to have to guess at that number after the decimal point. And so in order to do that, well, let me mark off where I think 2.5 centimeters would be. Let's say that 2.5 centimeters is approximately there. Okay, the length of the paper clip still falls short of 2.5 centimeters. And so if I had to guess, I'd say this is about 2.3 centimeters in length. Now, again, you might think it's closer to 2.2 or 2.4, and in the end, that all comes down to the uncertainty of measurement that we discussed in the previous tutorial. But for the purposes of continuing the discussion in this tutorial, let's just say that the paper clip measures 2.3 centimeters. Now, what about if I take a look down here? What if I try and repeat the measurement of that red paper clip, but now I'm going to use the second ruler? Well, once again, the ruler goes from roughly 0 to 10 centimeters, except this time I'm a little luckier because there are subdivisions between the whole numbers. And what that does is it allows my guess of the length of the paper clip to actually be a little bit more detailed. Now I can extend beyond the first decimal point, because if I take a look at the length of the paper clip, you'll see that it actually falls between the third and fourth subdivision between 2 centimeters and 3 centimeters. And if we count up the number of subdivisions between the whole numbers, we see that each subdivision corresponds to 1/10 of a centimeter, or 0.1 centimeters. So that would mean that this paper clip has a length of 2.3, but yet not exactly 2.3 centimeters, because if we take a look, the mark that represents the length of the paper clip here falls between the mark that represents 0.3 centimeters and 0.4 centimeters, between 2 and 3 centimeters. So that means it's 2.3 something. Let's say that it's 2.32 centimeters. Okay, notice that because that additional feature to the scale is there, those subdivisions are there, then I'm able to actually create a more detailed measurement. Now, instead of just being able to measure the paper clip to the 10th place, now I can measure it to the 100th place because of the presence of those subdivisions. And so when we consider measurements, we have to consider, okay, what portion of the measurement do I know to be 100% certain? Okay, well, let's have that conversation. Right here, if I take a look at the measurement that I made using the top ruler, I'm absolutely sure that the paper clip is longer than 2 centimeters. So I am sure of that 2 that I just put in the red box. However, I had to guess at the 3 that's behind the decimal point. And so this number right here is a digit that is unsure. So the 3 is an unsure or uncertain digit, and the 2 is a sure or a certain digit. Okay, let's have that talk about the measurement down here using the second ruler. Well, if you recall, when I was making the measurement, basically I was sure of the 2. I was sure of the 3 because of that scale, the subdivisions in the scale that I was using. Where I started to guess was the 2. And so here I have the 2, which is an unsure digit, or an uncertain digit, but I was sure of the 2 and I was sure of the 3. And so if you go back to the reading in the book, all right, we're told that when I have a measurement, the significant figures related to that measurement are all of the digits in the measurement that I'm sure of or certain of, and the first unsure or uncertain digit. Well, if that's the case, then that means right here, this first measurement has one sure digit and one unsure digit. So that means there are 2 significant figures. The measurement that I carried out with the bottom ruler, however, has 2 sure digits and 1 unsure digit. And so that would mean that there are 3 significant figures in this measurement. But that's all well and good if we're actually making the measurements ourselves to figure out the number of significant figures in the measurement. But what about if we're actually looking at data that we did not collect ourselves? We're looking at numbers that somebody else collected and we weren't there when the measurements were made. Well, then we can apply a set of rules to figure out the number of significant figures, and the more significant figures there are in a measurement, then the more certainty there is associated with the measurement, the more precision there is associated with the measurement. So if I'm looking at a set of numbers, all right, to figure out the number of significant figures, the first rule is simple. All right, the first rule tells me any digit that is not 0 is always significant. Okay, so any digit 1 through 9 is significant. Now, where it gets a little bit more complicated are zeros. All right, now there are 3 types of zeros when considering significant figures, though mathematically 0 still represents nothing. But in terms of determining whether we have a 0 that is significant and a 0 that is not significant, there's a few rules that we need to know. And like I said, there are 3 types of zeros associated with those rules. Here, any 0 in between significant figures, we call those zeros captive zeros, are always significant. So that means something like if I have 307, then this 0 between the 3 and the 7, that's a captive 0. And that would make this 0 significant. And since the 3 and the 7 are non-zero digits, then basically that means that we have 1, 2, 3 significant figures. Okay, now in rule number 3, they're discussing how we have space holder zeros, all right, in numbers that are less than 1. So that means if I have a decimal, any space holder zeros are not significant. These are also sometimes called leading zeros. So if I have a number like 0.025, both of these zeros are space holder zeros because the 2 and the 5 represent the 2 in the hundredths place and the 5 in the thousandths place, respectively. These zeros are just there to make sure the 2 and the 5 are in the right spot to convey the right decimal value. These zeros are not significant. So that 0 and that 0 are not significant, but the 2 and the 5 are, so I have 2 significant figures in this value. But what about if I have a number like 3,700, let's say? Well, these zeros that are at the end, these zeros are what we call trailing zeros. And trailing zeros are significant only if there's a decimal point in the number. So if I put a decimal point here, then these zeros just became significant. And that would mean that there are 1, 2, 3, 4 significant figures. Okay, but if I have 3,700 and I don't include a decimal point, then these zeros are not significant. Okay, so that would mean that I only have 2 significant figures. Sorry about that, significant figures in this value. Okay, whereas there were 4 in this one because of the presence of the decimal point. Let's take a little additional practice. Let's work on these 8 values. Okay, now here, let's take a look at number 1. Okay, I have a 5, non-zero digit, a 4, non-zero digit. Okay, but that zero is at the end of a number, so that's a trailing 0. But there is no decimal point. And since there's no decimal point, then this 0 is not significant. And so as a result, I only have 2 significant figures in the number 540. If we take a look at number 2, 9,620, well, this 0 after the 2 is also a trailing 0 with no decimal point in the number. That means the 9, the 6, and the 2 are significant, but the final 0 is not. So that means I have 3 significant figures in 9,620. Similarly, the zeros at the end of 200 without a decimal point are also trailing zeros with no decimal point. And so as a result, the only significant figure in the number 200 without a decimal point is the 2. And so that means I have 1 significant figure there. All right, now if I take a look at number 4, the number 0.25, well, right here I have a leading 0, and leading zeros are never significant, but the 2 is and the 5 is, and so in 0.25 I have 2 significant figures. Let's look at number 11. Now, if I have a value that's expressed in scientific notation, I don't worry about the exponential part of the number. I'm only going to evaluate the base that's in front of it. And so here, if you notice, I have 4 digits that are all non-zero digits. And non-zero digits are always significant. And so as a result, here I would have 4 significant figures. Okay, the number 77. Okay, both the 7s are non-zero digits, and so that would mean I have 2 significant figures here. For number 13, I have all of these leading zeros. Leading zeros are never significant, but I also have these 2 zeros at the end of the number. Those zeros are trailing. But if we take a look here, there is a decimal point in the value. And so because of that, then that means those zeros after the 9 are significant. So that means this 9 and these 2 zeros are significant, but none of the other zeros are. So that would mean I have 3 significant figures in the number in problem number 13. And then lastly, over here for number 14, I have 1, 2, 3, 4 digits that are all non-zero, so these are 4 significant figures in the measurement in number 14. So I'd like for you guys to try and practice this, so please do the follow-up assignment where you get a chance to actually try this for yourself. You're also going to have an assignment to do related to this in class tomorrow. And again, if you have any questions, by all means, do let me know, email, or talk to me in class tomorrow. All right, have a good night.